Okay. Good morning, everybody. I hope everyone's having a wonderful day. So first, before anything, today is Friday and next week is fall reading week. I must stress that we don't have class next week, so don't come to class next week. Listen, I love the enthusiasm, but we won't have lectures next week. However, I will be at my office hours if you need me. I'm always here to help, okay? So, that being said, remember about assignment 4, that deadline will be creeping up every bit closer after reading week, so I recommend you get started on that. So, that being said, I want to get to where we are today, so I'm starting with a new topic. It's going to share a lot of themes with last topic. So last day I showed you an algorithm for solving the minimum spanning tree problem. I showed you Prim's algorithm, and I talked a lot about different ways we could take Prim's algorithm and augment it to do all sorts of stuff. So today I'm going to be talking about a problem that's closely related to it. It's called the single source shortest path problem. Now, I'll explain what the single source part means in a moment. But for your purposes, you could think of this just as the shortest path problem. Usually people, if you tell them this is the shortest path problem, they'll pretty much quickly get what you mean. So I'm going to assume that my input graph G is weighted, undirected, connected, and its edge weights are non-negative. That means they can be 0 or more. So positive or 0. I'm going to define the following thing for you, is the so-called length or total cost or total weight of a path. I'll usually refer to it as the length of the path, but these are all synonyms for the same thing. So suppose I give you a path that's described by its edges. Now, keep in mind, you can also describe this in terms of its vertices. I just think it's a little easier to see when I describe it like this. So I'm going to have a path P, where its path is going to consist of vertices V0, V1, V2, V3, all the way up to Vk. The length of that path is very simply the sum of all of the weights. That's it. That's what the weight of a path is. The total weight of a path, or the length of the path. So that's all this is. It's just the sum of all of those edge weights along the pathway. We'll do an example in a moment. And what we're going to describe as a shortest ST path is a path from S to T with minimum length. So we defined a shortest ST path before, but we didn't do it on weighted graphs. Do you recall that? Do you recall that at all? We talked about an algorithm we can actually use to compute these. What was that algorithm? When I had not a weighted graph, it was just a graph. It didn't have weights or anything. What was the algorithm I told you that we could use to compute shortest ST paths? Does anybody remember? It starts with a B. It's going to be very important for today. It's remember my ventures to find the lost Temple of Awesome? Yeah, it's breadth first search. Breadth first search, exactly. Yeah, so if I were to give you just a graph where all of the weights are equal, you actually get that exact notion of the shortest ST path. So if I give you the input graph where all the edge weights are just 1 or just all equal values, you could use BFS and solve and compute a shortest ST path in this sense. Is that clear, everybody? So now I want to do is I want to study this where those weights can be whatever numbers as long as they're non-negative. So we're going to need a little bit more to do this. Now I'm going to present you a couple of very interesting properties that shortest ST paths have. I'm going to present these without proof just for the sake of time. So let me just move on over here. Let's move on over here. I had to give the camera a little nudge. I think the camera wanted a little nap too. So here are a couple interesting properties that ST shortest paths have. So the first one I want to point out to you is really, it's an interesting one in its own right. We will be studying this kind of property later on in this course. But if I give you some shortest path, if I look at some segment of that shortest path, I can tell you that that segment is in fact also a shortest path with respect to the vertices at the ends of that path. So that's one interesting property that shortest paths have. In particular, let me just go over here to this example over here. So just to be clear what a shortest ST path is, if I have S and T, so I know what S and T are here. The ST shortest path, or my shortest ST path, it goes here to there to here. But what I'm saying with property 1 is I could always examine, say for example, this vertex to that vertex, and I could tell you that if that edge is a part of the shortest path, then most certainly that itself is also a shortest path from that vertex to this one. That's what the first property is saying. We have a special name for this. It's called optimal substructure. We will be talking more about that when we talk later on about dynamic programming. So that's the first one. The second one, and this is probably the one that we're going to take advantage of the most beyond this, is the fact that because of this, there is actually a tree consisting of shortest paths from a source vertex S. So if you're wondering what single source means, what we're going to be talking about is I'm going to designate some vertex. I'm going to call it the source. I'll usually call it S. And what we're going to do is we're going to compute one of these shortest path trees. Now, I already described actually a shortest path tree when we were talking about breadth first search before, right? This is the more generalized notion of this. So what do I mean by that? If I have this tree, what's going to happen is that this tree is going to consist of shortest paths where I have my root being S. And what's going to happen is if I look at any vertex in this tree, which it's going to be a spanning tree, by the way. If I look at that vertex, if I take the path from that vertex back to S or vice versa, it will in fact be a shortest path. And this is true for every vertex that's going to be sitting in this tree. If you're wondering what one of these shortest path trees would look like, take a look at my example over there. The red edges is the shortest path tree. Notice that if I look at any one vertex, starting from S here, so I go from S to any other vertex, if I follow the red edges, that actually ends up being a shortest path from S to that vertex. So for example, if I want to go to this vertex right here, if I take this edge, which takes this one has weight 3, this one has weight 3, so the shortest path length here is in fact 6. Versus if I look at my ST path here, what's the length of the ST path here I have in my shortest path tree? Can somebody tell me? What's the length of that path from S to T? Remember, it's just the weights on the edges. So if I'm going from S to T and I follow the red edges, what is the length of that path? It's 5. Yeah, it's 5. So notice I take this edge, that's 3. Then I take this edge, which is just 2. So you might look at this and say, hey, look, Dan, this tree actually has all the information to compute the ST path that I want. That shortest ST path, it's in this tree. So the natural question you might have is, okay, well, if I have this, can I compute one of these shortest path trees of S, where S is the source? So what we're going to do, and this is how I'm going to cast the single source shortest path problem, is I'm going to assume I give you the graph under the conditions I described over there, and I'm going to give you some source vertex, and your job is to give me the shortest path tree of S. So that's going to be actually how we're going to describe the single source shortest path problem. If you can solve that problem, you most certainly can solve computing the shortest ST path, right? Especially if I store any information like I did last day, like with my minimum spanning trees. Remember I had this parent, like my predecessor? I'm going to do the same exact thing, where I'm going to do that so I can get that information right out of this tree. So you're going to see some very interesting and quite fascinating connections between Prim's algorithm and the algorithm I'm going to show you, even though they're two different problems. They have very similar structures to them. And it all builds around these two properties. So first, does everybody understand the game plan? I'm going to compute one of these shortest path trees. That's going to be my goal. And just as a reminder, if all of the edge weights were equal, this would be the exact same concept I showed you when we were talking about breadth first search. So this is just more general than that. In fact, that fact in itself is actually going to help us get some ideas of how we're going to design the algorithm. So if we're okay with this, is it okay if I move on over here? Give me 2 thumbs up if we're all good. Okay, I think we're good. So let's head on over here. I'm going to define the single source shortest path problem, seeing as I've given you all the bits and pieces. And now then we're going to talk about how we're going to solve this problem. So you're going to notice that I presented those two properties without proof. I'm hoping that I've given you enough of an idea about this that hopefully you're okay with accepting that. An easy way you can show these properties, by the way, is often through contradiction. Is you start off with that first property and you try to prove it by contradiction. And then you just simply say, hey, look, you can actually do something quite similar to the cut property, if you're curious. That proof I showed you before, except you could invoke contradiction to get the thing to work. So let's proceed. So here I'm going to define the single source shortest path problem. Single source shortest path. So this is what I'm going to define as the single source shortest path problem. Let me get a different marker. This one's acting a little funky. It's being a little funky for us. And not the good kind, the kind where I do a dance, like me just doing a dance like this, like that. It's not like that, unfortunately. So what we're going to do is we're going to compute, and this is much better, compute a shortest path tree from source S to every other vertex. That's what we're going to do. We're going to figure out that shortest path tree. Now, that brings me to talking about the algorithm in question today. We're going to talk about an algorithm called Dijkstra's algorithm. This is a classic in the combinatorial optimization community. So, if you're wondering, this algorithm sort of came about in the late 50s. There's sort of a fun story around this algorithm if you find yourself curious about exploring this idea, but it was developed by Dijkstra. Sorry, I'm having a fun time here. And one of the computer science pioneers in the area of algorithms. So what we're going to do is we're going to take two ideas and kind of slam them together. So the first one, as I've kind of alluded to at this stage, is that we're going to try to use breadth first search. So I'm going to take the idea that we had for breadth first search. And I'm also going to try to take some of the mechanisms that I had from Prim's algorithm. So what we're going to do is we're going to take, let's So we will take, so naturally the revenge of the blob is going to happen. Just a heads up, we're going to come back to the blob, but it's just going to, the blob's going to behave a little differently. We will take two ideas we've seen before. So we're going to take advantage of those two properties I wrote up earlier. So the first idea is that we know how to compute, shortest path trees, right? We know how to do that. Maybe we don't know necessarily how to find this one over the more general case. So we're going to need something else to help us with this. So we know how to do this on weighted graphs. So these are graphs without weights. Remember, we can use BFS to do this. And I lost my little turtle friend. My turtle friend went on reading week, okay? Kind of escaped early. And now here's the other one. And I'm going to take the idea that we had from Prim's algorithm, and I'm going to generalize it. Because if you think about it, if I tell you, okay, so remember my picture I had over there, where what I did is I had a shortest path tree. Now you'd agree with me that if I had some shortest path, say if I have it from one vertex to another vertex, and I would like to extend to another edge that gets me closer to some vertex, say T. What would be the most natural choice to make to extend my path by an edge? And I want you to think back to something like Prim's algorithm, or what we did there. It's not exactly the same idea, but it's very similar. Does anybody have any ideas? Well, think about it. So remember, in Prims, we always selected edges in a very specific way. But remember, we only cared about always picking the least weight edge. But remember, we now want to compute the shortest path from the start, our source vertex, to any other vertex. So what can I do with my idea ever so slightly? What kind of edge should I pick? What kind of edge? So in Prims, I always select the least weight edge from one side of the cut to the other. What kind of edge should I pick this time? And I'll give you a tip. It's very much the same mechanism, but so it's like UMin, like in Prims, but UMin needs to be a little different. We don't want it just to be the smallest edge weight. We want it to be not just that, but we're very close. We're very close. So for example, if I have some path, I don't know, just for hypothetical purposes. So suppose this is S, and I want to get to some vertex T. And suppose I have a bunch of different choices that I could take that could get me to T. And all of these have edge weights to them. And there's some way I can get to T. If I were to pick from these three edges, which one should I pick? And remember our definition of the length of a path. The shortest, exactly. Because remember, the first property I told you is every shortest path. If I give you a shortest path, it's composed of shortest paths. So if I give you this vertex, say if I look at this vertex and I pick the edge such that it is a shortest path, then most certainly I've extended it correctly. So that I have one more edge that will get me closer to a shortest path to T. So that's all we have to do. We just take advantage of the fact that our shortest paths are comprised of other shortest paths. And by picking always the one that's closest to us from our source, we can guarantee this. This is why I'm going to tell you that Dijkstra's algorithm is, for example, a greedy algorithm. Greedy algorithms, the way greedy algorithms work is they always make the best choice at that given time. In this case, we always are going to select the vertex that has not yet been included in our, if you think of it as our cloud or blob. And it's always going to be the one that is closest to the source. See, now the reason why it's different is, so why we don't pick the least weight edge, it's very similar, but we have to be very careful. So when I pick a least weight edge here, we do it with hindsight because of all of the information we computed up to this point. So we're going to need to take into account the distance that we've traveled up to that point, but we're always going to typically pick the one that's going to be the closest to us, but we want to guarantee that the one we always select is going to be the one that's closest to the source, because we always can rule out the possibility that we could always find one a little later on. I'm going to give us a mechanism to do this. So I'll hopefully elaborate the difference between just picking any old least weight edge and the one that's going to get us to the next closest vertex. So it's just the order in which I pick the vertices that's really going to make the big difference here. So I'm going to take, so the other idea is that perhaps the idea when computing MSTs generalizes. So in this case, by the way, just to be clear, your idea, it would work, but the problem is we want to make sure we always are building shortest paths every time we do this. So if I were to pick any one of these, typically it's going to end up being that least weight edge. But we need to be very careful about it because there's always sometimes a weird contrived example that totally breaks it apart. So there is such a thing, well, I'll say it does, into what is called an edge relaxation. This is going to be the main mechanism for which we're going to update those D values like I had in prims. So remember, in prims I had that D value that's going to tell me, oh yeah, this is the one I'm always going to keep in mind. In prims, I always keep track of the least weighted edge, right, that I have so far. This D value is going to mean distance now. So its meaning for the D makes a lot more sense, does it now? Yeah. And it's also going to have the parent just like I did before. So I'm going to use this mechanism to update how close we can be to another vertex. And the idea is very simple. I'm always going to make sure that I always pick a vertex that's going to be closest to the source. And naturally, by picking the edge that connects those two endpoints, we're going to end up getting a shortest path that's going to extend by one edge. So let me describe what the edge relaxation is. And it's surprisingly simple. And you're going to see the same idea here when I actually show you Dijkstra. So we're going to keep track of a so far shortest distance from S to each vertex. And that's what's going to be, we're going to call it v.d. So that's exactly like the way I've talked about this the other day. So this is the best path length found so far. Because remember, when we computed minimum spanning trees, we didn't really take into consideration the other edges other than it's a least weight edge, right? We have to be more careful here. because there may be other edges that could lead me to said vertex. That's why I'm saying you can't just pick the least weight edge, because there could always be some way that all of these edges add up to some path length, but by picking this one at that given time may give me some contrived counterexample. It's going to cause me problems. In this case, it's okay. But like I said, this is just simply a pathway. It may look very different than this, where you might have an alternate path. Remember, there could exist an alternate pathway that could come all the way around and be like, I can go over here too, but I could use a shorter distance to do it. That's why we have to be a bit more careful than we were with prims. So we're going to have v dot d. So we're going to consider an edge E with endpoints uv, where u is the vertex, most recently pulled into the blobber cloud B, and V is not in B. So to update this distance, we're going to do the following. So to update V dot D, we're going to do what we call a relaxation. We're going to relax edge E. So that's the phrase that people typically will use. They say they relax edge E, and it works like this. We're going to have an if statement. If U dot D plus the weight of the edge from U to V is less than V dot D, then since I found that means I have found a closer way of getting me to V. If this is in fact true, if that's the case, then I'm going to update V dot D to be in fact U dot D plus that weight. So just to yes. Thank you. Yeah, so this is in fact a V. So that's a V right there. So V dot D, sorry, that's U. My apologies. This is U. This is in fact a U. My apologies. U dot D plus the weight of edge E is less than V dot D. Then you're going to update V dot D to be U dot D plus the weight of edge E. Does that clarify that? Yeah, so notice that this is just simply saying if I found a closer way of getting to V to the source, I update it. That's all it really says. There's no voodoo or any magic here. That's all it is. That's all it's saying. So are we okay with the idea of the edge relaxation? So a very natural place for me, you're going to see this appear in prims. So remember in prims, we had that step where I examine all the incident edges, right? All I'm going to do is I'm going to replace that update I did there, where I examine all the incident edges, I see if I have a better least weight edge. I'm going to replace that with my edge relaxation. And this should look hauntingly like prim's algorithm. So I'm going to first write out the pseudocode for us, and then we'll do an example, okay? Just to really highlight the fact that this is really not that much different. It's just that this algorithm takes advantage of similar properties. In fact, some people, when they teach this algorithm, they sometimes show you Dijkstra first, then they show you prim's algorithm. I'm just doing it the other way around, but they're very closely related algorithms, but it's only because the properties that they have are closely related. it's not really that fundamentally that minimum spanning trees and shortest paths are like tied at the hip, which they do have very similar properties though, which, like I said, you could say very similar things about minimum spanning trees, right? If I give you some subset of the vertices and I ask, oh, is that a minimum spanning tree? Indeed, you know how to extend that minimum spanning tree to another vertex. You would always select the least weight edge, right? So that's what you would do every single time in prims. The difference here now is I'm always going to select the closest vertex that is not a part of the blob, okay? So this is going to describe what we call a greedy algorithm. Greedy algorithms, they always take the best choice given at that time. Usually this is described as a locally optimal choice. And the goal in a greedy algorithm is to always select the locally optimal choice and hope and guarantee that that always leads to a globally optimal solution. So I'll talk more about greedy algorithms depending on how much time we have after this. If not, we'll talk more about it when we get back from reading week. So let me write out Dijkstra. And like I said, you'll almost feel like you're writing down what I wrote last day. So here's Dijkstra. So I give you an input. So my input's quite simple. The input is a connected. The input is a connected, undirected, weighted. Like I said, there's a lot of things I'm describing here. A connected, undirected, weighted graph. G is equal to VE. And by the way, remember that the weights here are non-negative. And also I have the source vertex S. And the output is going to end up being, the output is it's going to be the shortest paths from S to all vertices. Just to be clear what a shortest path tree is. To all vertices. So if you just want one of the paths, all you have to do is you're going to take the information you get from the way this algorithm is going to be laid out. So I'm going to do the same exact thing I did at the beginning of prims, where I'm going to set up all of these D values and parent values for each vertex V of G. We're going to do the following. So I'm going to have each my V's. I'm going to go V dot D is going to be assigned infinity. And V dot parent is going to be null at the beginning. And now, quite like prim's algorithm, I'm going to assign the source's D value to be 0. Now, it's for a different reason this time. Is that the distance from S to itself is what? Can somebody tell me? What's the distance between S and itself? It's 0, exactly. So that's why I'm going to assign SD to, this is going to be the shortest distance from S to S. And now I'm going to do the exact same setup I showed you last day. Remember I showed you that priority queue-based implementation? I didn't quite finish everything I wanted to do there, so I asked you to read a little bit further. But I wrote out the pseudocode regardless. You're going to look at this and be like, Dan, you basically wrote that last time. and I hope that that's the intention, that's hopefully the reaction you should get from this. Let priority queue contain all the vertices V in V. And I must stress that each V dot D is the key of an entry or element. So if you're using v.d as the key, and remember, in this approach, we're going to make sure we update that v.d if ever we need to. And that's why we have that decrease key operation. So that we can go into the heap, we can pull out pieces and be like, okay, I need to update this particular vertex's d value, and I need to make sure that gets translated into the heap structure so it updates. That's why we're going to need this information. And that's why we need the decrease key operation, which is going to also come up again. So naturally, you can also technically take this a little further. So I'm just going to simply say, while Q is not empty, you're going to do the following. So now we have umin like before. Umin is going to be assigned q.remove min. So this is what's going to pull umin into the blob or cloud, wherever you like to think of it. If you prefer before the imagery of a cute fluffy cloud just sitting over that vertex, that's also cool. If you want to think of the morbid blob that just kind of gobbles up them, that's also okay too. You can also think of it just as a set of vertices. That's all you have to really think of it as. So we're going to dump out this priority queue until there's no more vertices in there anymore. So naturally, you could, like I said last time, you could have a place where you mark the vertex, but we don't need to use those at all. So I'm just going to keep this very simple. So I'm just going to proceed to just checking each one of my incident edges, just like I did last time. For each edge, umin. So each edge incident on umin, you're going to do the following. This is where we're going to do our edge relaxation. And this is the part that's going to be different. All I'm going to do is substitute that part where I examine and see if I have a better least weight edge with the edge relaxation I wrote over there. That's all it's going to be different. So if umin dot d plus the weight of umin v, meaning the edge that consists of umin v, is in fact less than v dot d, that's when you know you're going to need to update that d value for the v. So let me just underline my if there. Now, here's those three lines again. v dot d is just going to simply be umin dot d plus the weight of umin v. Then I'm going to apply decrease key, q dot decrease key, and I'm going to apply that on v, and I'm going to update its key to be v dot d now because I just updated it, and I'm going to update the parent of v. v dot parent is just going to end up being umin because we found a shorter way of getting to v. And I think I need 3 closed curly braces. One, two. Sort of running out of space here, but that's Dijkstra right there. So this is the pseudocode for Dijkstra. If you run through the time complexity analysis, it will exactly match the one for the priority queue implementation I had showed you last day. You can show that this, for example, if I use a binary heap, I can show that this runs in big theta m log n. Like I said, the time complexity analysis is not very interesting here because this does everybody see it? That this is essentially what I showed you last time, except I just changed an if statement here and just a couple of other, I think only a couple other small things, but they all are just things that take either constant, they basically take constant time, right? So is everybody okay with this? Why not n squared? Well, remember, I'm saying that this is a priority queue-based implementation using a binary heap, and I should stress that this is represented using an adjacency list. if you were to attempt to use this binary heap approach with an adjacency matrix, you may end up with something like big O of n squared log n. But you can classically take the algorithm and you could still do the exact same thing you did with prim that first time I showed you. You can still make it big O of n squared. In fact, I would recommend that if the graph is very dense. So just to be clear, this is not going to be, well, mathematically it's big O of n squared, but it's not really big O of n squared. It's big O of m log n. But what I'm saying is you can take this algorithm, you just go to the first presentation I gave you of prim's algorithm, you make the couple changes I have here, and you can show that that runs in big O of n squared. But I'll let you take a look at the notes because I have to do the example. So let me proceed here. So let's proceed. I want to do an example just so you can get a flavor for this. Like, I'd love to talk about the analysis for the last bit of time in class today, but I really want to make sure you see this example. But yeah, all the details are in the notes for how you do the analysis here. It's identical to the way prims works. In fact, even the things I stated about the Fibonacci heap, for example, last day, that also holds here too. So you can get those same running times that we had for prims for Dijkstra too. So let's do an example. So let me draw out a graph. So let's do an example. So I'm going to take a graph that's, I think this is either the same or it's very similar to the one I had last day. So I'm going to number these 1, 2, 3, 4. And this time, make sure it's a 5. Make sure that's written as a 5. The weights from 2 to 5, that's 1, 4, 3, 3, 2, 1. And I'm going to again have my d value and my parent value for each one of these. D, parent. And just based on the mechanism that we did last day, you should be able to see how you can actually get the path by just following the parent references from T. So if you give me a T value, you can easily augment Dijkstra's algorithm if I gave you some T value to actually get the path. So D parent. There, I got all my D's and parents. When this starts off, I'm going to assume that the D's are all infinity, and the parents are, in fact, null at the beginning. Remember, that's what the first loop does in Dijkstra. Now, I'm going to pick 4 to be the starting vertex this time. So the source is going to be 4 in my example here. So just keep that in mind. So when I start this up, what I'm going to do is I'm going to have it where the S, since this is S, just to illustrate, make sure it's clear, this is S. Its D value is going to be 0. That's what I set up before I enter the while loop after I've dumped all of the vertices into my priority queue. And now what I'm going to do is go through each one. And since the key in the priority queue is, in fact, these D values, the very first one I'm always going to pick is the start. Because every other one has D value of infinity. Did everybody see that? So what I do is I'm going to now remove from my priority queue S, and then I'm going to now go through each of my incident edges and apply the edge relaxation. So that being said, you might ask, Dan, how does this work? Well, I want you to think back to last day when I talked about the blob. Now remember the blob? The blob would gobble up the least weight edge in Prim's algorithm, but it was always the one with least weight edge from wherever the blob was. Now this blob in particular is really lazy, and I mean really, really lazy. This blob will always gobble up the next vertex that is closest to where it started. Does everybody get the idea? So the blob is starting here at 4. So it's gobbled up. So it's gobbled up 4 here. And now what I'm going to do is look at all my incident edges on 4 and see if I can update their D values, meaning I have a closer way of getting to them. And the blob is always going to pick the closest vertex that is not in the blob. So just remember that. It always picks the next closest vertex not in the blob. Gobble, gobble. The gobble, gobble part's just for me. That's just for me, okay? So, anyways, now I look at my incident edges. And remember, the next closest vertex, that's the information stored in these D values here, okay? So, I have the edge here with weight 1. So I'm going to update that to be 1 because it's definitely less than infinity. And its parent is indeed 4. And I can get also to 3 via this edge. So the distance I take to get there is 2. And its parent, of course, is also 4. And I'm done for this iteration of performing the edge relaxations. So it's not very interesting yet. This looks kind of like Prim before. So let me just quickly finish this up. And then we're going to end on this. So if you have to go somewhere, all I'm going to do is finish up this example. So let me just wrap this up. So which one should I pick next? I should pick the 1, right? Because D is 1. That's less than 2. So that's the smallest one. In fact, that's going to come out of the priority queue. Then what I'm going to do is the blob's going to gobble that up. Like this. Gobble, gobble. And then it looks at all the incident edges. Now, the thing that makes this different with the edge relaxation is it keeps track of this D value now. So now, instead of it being where I just simply say, okay, well, it's that dot D, and I look for the smallest one, now I have to keep in mind what this is at this stage. So what I do is I look at 1's D value, so which is 1, and I add to it the weight of the edges that are incident on it. So in this case, I look at each of my incident edges that are here. So notice that, okay, so 3 plus 1, that's 4. That's definitely not less than 2. So we don't update that. However, here I can have 1 plus 3, which that's 4. Meaning I found now a shorter way of getting to 2, because I haven't really found 2 yet. So, and it's all my incident edges. Notice you're not going to go back over here because it's shorter to go to 4, right? You already went there, and I've already dumped that out of the priority queue. So you're never going to revisit S again, or any other vertex that's in the blob. So now, which one should I pick next? I picked the one with the smallest D value, right? Remember, the blob is very lazy. I picked this one, right? Perfect. Yeah, we picked 3. 3's going to go in the blob. Here we go. So now we have to look at our incident edges again. Well, that's already in the blob, but notice it's 1, 0. Here, okay, 2 plus 4 is 6. So that's most certainly going to be better than infinity. And I have 3 here. So now I have my next one. My choice is either 2 or 5. 2 or 5. Which one should I go for? Remember what the blob does. It's very lazy. 2. Yeah, it goes to 2. Perfect. Goes to 2. Okay, and then I look at all my incident edges. Okay, I have 4. So 4 plus 1 is 5. That's indeed going to be less. So most certainly I have this. And naturally, this is the last one you're going to have here, so I'm just going to pick 5. And 5 joins the whole blob. The blob has gobbled up the entire graph. Hungry blob. Sorry, I'm getting really excited here. This blob business is very exciting. So now I have all of these. Now, if you look at how I had I made all these choices, you could say, okay, well, if you're wondering when I knew where these were going to happen, they happen actually in the exact same points where they happened in prim. If you're wondering when these edges are determined, if you're just curious about that, they happen actually whenever I remove one of these and I select it as human, I know actually the information about the edge. It's the exact same way we had it in prim. You just look at its parent. So notice that we have this edge, and then lastly we have this edge, and that's the shortest path tree. So if you ever wanted to get the shortest path, say from 4 to 5, you could just follow from 5 here, which that would be what t is. You go to the parent of 5, that's 2. The parent of 2 is 1, and the parent of 1 is 4. Wonderful, wonderful. Are there any questions before we go? And I want to apologize for taking extra time here. If there aren't any questions, I will be around a little later. I'll be hanging around here. So if you have any questions after class, just come ask me here. I want to say thank you very much and have a good reading week. And I'll see you later. And thank you for your time. I really appreciate it. I'll see everybody later. Have a beautiful day.